All right, so we're on the very next page of our notes for section 5.1 to 5.2. So in examples, let's say that we have a jar of marbles and we have 3 red, 17 blue, and 19 green. What we want to know is what's the probability that we pull out a red marble, a blue marble, and we want to express this as a fraction, a decimal, and a percentage. So the probability that we pull out a red marble, well, we have 3 different red marbles, so we have 3 ways we can do that. Out of, let's see, 3 plus 17 plus 19, so that's going to give us 39 total possibilities here. So probability of pulling a red marble is 3 out of 39. The probability of pulling out a blue marble, well, we have 17 ways we can pull out a blue marble, since we have 17 of them, divided by 39. And we also wanted to write these as a fraction and a decimal. So when we write these as a decimal, we're going to take 3 divided by 39, and we'll just round to, let's see, 4 decimal places should be good. So that's going to be 0.0769, which when you write it out as a percentage, you're going to move that decimal place 2 to the right. So that'd be 7.69%. Same thing with the blue marble. We're going to take that 17 divided by 39, and we'll also round to 4 decimal places. So 4359, which again, as a percentage, we're going to move it 2 over, so that would be 43.59%. So when you guys are doing the homework, make sure that you're paying attention to what the question is asking you and how it wants you to phrase the solution. If it wants it as a fraction, decimal, or percentage, and how many decimal places. All right, so we're going to be looking at and or probabilities, and we're going to be looking at 2 subsets of those. So there's going to be independent and dependent. So first we're going to be talking about independent events. So what these are events that don't depend on one another. So for example, if I flip a coin, okay, if it comes up tails, that's not going to have any effect on whether the next one comes up tails. So for example, let's say we want to look at the chance of rolling a fair die and getting a 4 and then flipping a coin and getting tails. So notice these 2 are independent because one doesn't depend on the other. The coin flip doesn't depend on the die. So let's go ahead and draw a tree to help us. So we're going to have 1, 2, 3, 4, 5, and 6 for our dice. And for each one of these, if we were to roll a 1, the next possibility for flipping a coin would be heads and tails, heads and tails, heads and tails, heads and tails. Okay? So if we count all the different possibilities in our sample space would be this side. So we could get a 1 and a head, a 1 and a tail, 2 and a head, 2 and a tail, 3 and a head, 3 and a tail, etc. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So we have 12 possibilities. And we want to count how many times the outcome of getting a 4 and getting tails happens. So getting a 4 and getting tails, well, that only happens once. So that would be our probability. Another way we could word this is, or another kind we could do, is what's probably getting tails and an even. Okay, well, we still have a sample size of 12, and how many times do we get an even number and tails? So let's see, 1's not even, 2's an even number. We'll do this in a different color. 3, 4 isn't even, 5 is not, 6 isn't even. So out of all 12 possibilities, there's only 3 that will give us tails and an even number. So when you have and probabilities, what you can do if they're independent is you could take the probability of one thing happening and multiply it by the probability of the other happening. So in the previous example, the probability I get tails, okay, times the probability I roll a die and get an even, the probability I get tails is 1 and 2, times the probability I get an even. So let's see, I have 3 evens out of 6 die total, or 6 options. So that would give me 3 out of 12. So the same thing I got above. So these are nice when you have just weird empirical data. So for example, if there's a 30% chance of rain and an 80% chance that Andre wears his shoes with a hole in them, and let's say that these are independent, so Andre never checks outside, he just randomly grabs a pair of shoes, okay? We want to know what's the chance that it rains and he wears his bad shoes. So the probability of rain times the probability that he wears his bad shoes is going to be 0.3 times 0.8, so 0.3 is 30%, 0.8 is 80. So those together are going to give us 0.24, or a 20% probability that he does this. Now we're also going to look at dependent events. So this is where one does depend on another. So let's say we have a jar with 10 red marbles and 10 blue marbles. What's probably we pull out a red marble and then a blue marble when we put that red marble back? So the probability that we pull out a red one times the probability we pull out a blue one. Okay, what that would be is that would be 10 out of 20 times 10 out of 20, which would then give us, 100 out of 400, which would just be a fourth if you simplified it. However, if we pull out a red marble and then one blue marble without replacement, well, that changes things. So the probability that we pull out a red marble times the probability we pull out a blue marble. Well, for this one, I originally have 10 red marbles and I have 20 marbles total. On this one, if I don't put that red marble back, then what happens is I still have 10 blue marbles, but now I only have 19 marbles total. So that will give me 100 out of 380, right? So it cuts down our probability a little bit. So whenever you're doing probabilities that have dependent events, that means one depends on the other one, what you're going to do is similar to the last one, but when you multiply, you have to assume that A has happened. That means that you have eaten or you haven't put something back. So for example, what's the probability of randomly drawing one red M&M and then a non-red M&M from a bag that contains 8 M&Ms? So the probability of pulling out a red one, and then probability of not pulling out a red one. Well, we have 8 red M&Ms out of 40 total. And then what we do is that we eat it. We eat that red M&M. And then we want to know what's the probability that we pull out one that's not red. So we have 8 red M&Ms and 40 out of 40 total. So that means that we have 32 that aren't red out of, remember we ate one, so that's going to be out of 39. Alright, so whatever that number is would end up being our probability. So I'll do that math real quick. That gives us a probability of 32 out of... Alright, the next one is where we have either or probability. So when you think of an either or probability, what that means is that you're happy if you get one or the other. So for example, if I send you guys to the grocery store and I'm like, hey, can you either get me cookies or ice cream? If you bring me cookies, I'm totally happy. If you bring me ice cream, I'm totally happy. If you bring me cookies and ice cream, oh my gosh, I'm over the moon. So, first of all, we're going to look at non-overlapping or mutually exclusive events. So you can think of this as you can't buy both at the same time. So let's say that you only had enough money to buy me cookies or ice cream. That means that I couldn't get both, which bums me out just thinking about it, but whatever. So, for example, what's the probability of rolling a fair 6-sided die and getting a 4 or a 6? These are mutually exclusive because there's no way you can roll a die and get a 4 and a 6 at the same time on the same die. So if we look at our sample space, well, we have 6 different possible outcomes. And for the desired outcome, we have 1 and 2. So we have 2 out of 6, which would give us a 1 in 3 possibility of seeing a 4 or a 6. Okay. All right. So we are just going to go ahead and skip this example. But if you have overlapping events, what you can think of is you can think that you're going to add the probability of one plus the probability of the other. Now, it gets a little bit more complicated if you start looking at events that do overlap. So let's suppose we want to find the probability of pulling either a jack or a red card from a deck of cards. Well, if we calculated this, how many jacks are in a deck of cards? 4 out of 52. Plus, how many red cards are in a deck of cards? 26 out of 52, which gives us 30 out of 52. Now, the issue with this is that it's wrong, but we want to see why. Now, if we list out all the different possibilities for the deck of cards, I'm going to list them out really quick, and you guys can just, you can write them down or you can just believe me. Either way is fine. So they will appear in just a second. Alright, so I listed out all the different cards that we have, and we have 52 altogether. Now, what I'm going to do is I'm going to go through and I'm going to count all the outcomes I'm okay with. So, if you count all the red cards, there's going to be 13 hearts and 13 diamonds, which are going to give us 26 total. Now, add that to the jacks I'm okay with. So it's 26, 27, and 28. So I only actually have 28 cards that satisfy either pulling out a jack or pulling out a red. So why was this number wrong? Well, here's why. When we counted, we started off by counting the jacks. So we had 1, 2, 3, 4 jacks. And then we added to that all the red cards. So we had 13 of these red cards and 13 of these. So if you look carefully, what you see that we did is that we counted these jacks that are red twice. So when we do overlapping events like this, we have to count all of the probabilities of A, all the probability for B happening, but then we have to subtract the double counts that we did. So, for example, let's say that we want to choose a person to serve as president of a club, and we have 4 women and 4 men. 3 of the women and 1 man are members of the Newton Party, while the rest are belonging to the Leibniz Party. What is the probability that we choose either a woman or a member of the Newton Party? So the probability that we choose a woman or a member of the Newton Party is going to be the probability that we choose a woman plus the probability that we choose somebody of the Newton Party, but we have to subtract those people that we double counted that belong to both groups. So, out of the 8 people, 4 are women. Out of the 8 people, we have 3 women and 1 man that belong to the Newton Party, so that'd be 4 out of 8. Now, if we just stopped here, we would have 4 8s plus 4 8s, which would give us 100%. So that means that there's a 100% probability that we choose either a woman or a member of the Newton Party. That's not true. So, the error that might have occurred is we forgot that we have to uncount this double count. So, we have to uncount the probability that we choose a woman who's also a member of the Newton Party. So we have 3 women part of the Newton Party, so that'd be minus 3 out of 8. And we would get 5 8ths for our solution. Alright, this example problem below is going to be in the next video. Okay, that's totally optional. I really highly recommend you watch it because it's going to help you out with the homework a super great deal. So that's coming up in the next video.